We built it to answer our deepest questions. $10 billion, 30 years of engineering, a golden mirror the size of a tennis court, folded like origami, unfolded in the dark of space with a precision that made engineers hold their breath for weeks. We built the James Webb Space Telescope to see the beginning of the universe, to look further back in time than any instrument ever built, to witness the first galaxies, the first stars, the first light after the darkness of the cosmic dawn. And it worked. It worked better than anyone dared hope. The images that came back were extraordinary. Ancient galaxies resolved in detail that took the breath away. Atmospheric chemistry of distant worlds decoded from starlight. The universe's earliest epochs unveiled in wavelengths of infrared light that no human eye could see, but every human mind could marvel at. And then, as the data poured in and the scientists bent over their screens and began to analyze what they were seeing, something happened that nobody fully expected. The answers created more questions. Not the comfortable kind of questions, not the loose ends that any successful mission generates, the fine details to be tidied up by the next instrument in the next decade. Deep questions, foundational questions, questions that reach all the way down to the bedrock of our understanding of how the universe was born, how it evolved, and what it is made of, and find that bedrock cracked in ways we do not yet know how to repair. James Webb did not just see the universe. It saw things in the universe that our best models say should not be there. And despite years of analysis, thousands of research papers, and the best minds in cosmology working the problem, some of those things remain unexplained. This is the story of the mystery James Webb cannot explain, and it goes deeper than any telescope has ever gone before. Before James Webb launched, cosmologists had a story. A confident, well-tested, mathematically precise story about how the universe evolved from the hot, formless plasma of the Big Bang into the structured, galaxy-filled cosmos we observe today. The story went like this. In the first few 100 million years after the Big Bang, the universe was dominated by dark matter and hydrogen gas. Slowly, gravity pulled the dark matter into filaments and halos, invisible scaffolding. Into those halos, ordinary matter fell. Hydrogen gas accumulated, collapsed, heated, and ignited into the first stars. Those first stars were enormous and short-lived. They burned through their fuel in a few million years and exploded, seeding the surrounding gas with the first heavy elements. From those enriched gas clouds, the first small proto-galaxies formed. Over hundreds of millions of years, those proto-galaxies merged and grew, building the larger structures we see in the universe today. It was a bottom-up process. Small things first, large things later. Time was the key ingredient. You needed time for gravity to do its patient, grinding work. Massive, mature, fully structured galaxies should not exist in the very early universe. There simply had not been enough time for them to form. James Webb looked at the early universe and found massive, mature, fully structured galaxies. Not hints of them, not proto-galactic fragments taking their first uncertain steps, fully formed, enormous, structured galaxies containing hundreds of billions of stars, as many as the Milky Way contains today, existing when the universe was just 500 to 700 million years old, some even earlier. Jade's GS Z13-0, the most distant confirmed galaxy, existed when the universe was just 320 million years old, and it was not a fragile infant, it was already substantial. When these discoveries were announced, the response from the scientific community was not polite enthusiasm. It was something closer to controlled alarm. Papers were published with titles using words like unexpected, surprising, tension, and in one case, the phrase impossible early universe appearing not in a tabloid, but in a peer-reviewed scientific journal. Because the implications are real. If galaxies formed this large, this fast, this early, then something about our model of galaxy formation is fundamentally wrong. Either the rate at which stars form in the early universe was dramatically higher than any simulation predicts, or dark matter behaves differently at early epochs than our models assume, Or there is some process or ingredient operating in the early universe that we have not identified and are not accounting for. Or perhaps the most unsettling possibility of all, the standard model of cosmology, lambda cold dark matter, the framework that has guided cosmological research for 3 decades, may need not just adjustment, but revision at a level that changes the story from the first chapter. Scientists are not panicking, but they are working very hard, and the galaxies are still there, still unexplained, still sitting in the Webb data, enormous and early and patient, waiting for the theory that can account for them. The impossible galaxies are not the only thing Webb cannot explain. There is a number, a single foundational number that describes one of the most fundamental properties of the universe, how fast it is expanding. It is called the Hubble constant. And James Webb was brought into one of the most significant scientific disputes of the modern era, a dispute that has been running for years and that Webb was specifically tasked with helping to resolve. Here is the problem. When scientists measure the expansion rate of the universe using the cosmic microwave background, the ancient light from the early universe, our best record of the cosmos in its infancy, they get one value, approximately 67 kilometers per second per megaparsec. When they measure it using local methods, Cepheid variable stars, type 1a supernova, the actual distances and velocities of nearby galaxies, they consistently get a higher value, approximately 73 kilometers per second per megaparsec. 67 versus 73. This is the Hubble tension. And before Webb launched, some scientists hoped it might be a measurement error, specifically an error in the local measurements. The chain of distance measurements used to determine the local Hubble constant involves multiple steps, each step using the result of the previous one as a foundation, and any systematic error at any point in the chain would propagate through and bias the final result. Webb was the tool to check the chain. Its infrared vision and extraordinary sensitivity allowed it to independently verify the most critical link in the distance measurement chain, the Cepheid variable stars used to calibrate cosmic distances. The results came back in 2023. Webb's independent measurements confirmed the local Hubble constant measurements, not 67, closer to 73. The tension is real. It is not a measurement error. It is not an instrument calibration issue. It is not a systematic bias in the data that better technology can fix. It is a genuine, confirmed, cannot be dismissed discrepancy between two different ways of measuring the expansion rate of the universe, which means one of two things. Either our understanding of the early universe, the physics that determines the CMB measurement, is wrong, or our understanding of the late universe, the local physics that determines the local measurement, is wrong, or both are wrong, in different ways for different reasons. Webb confirmed the problem. It did not solve it. And solving it, finding the new physics or the overlooked ingredient or the revised assumption that reconciles 67 with 73, is now one of the most urgent problems in all of science. Because the Hubble constant is not just a number. It is the heartbeat of the universe, the fundamental rate at which space itself is stretching. Get this number wrong and every calculation that depends on it, the age of the universe, its size, its composition, its fate, carries that error forward. Two measurements, one universe, two different answers. James Webb made it worse, in the most productive, most exciting, most necessary way possible.
The impossible galaxies and the Hubble tension are the largest mysteries Webb has handed us, but they are not the only ones. In the data flowing back from Webb every day, there are smaller mysteries, anomalies, detections that raise eyebrows and prompt long discussions, and generate research proposals for follow-up observations. They do not all have names yet. Some of them are galaxies whose chemical compositions do not match what the models predict for their age. Galaxies in the early universe that contain heavy elements, carbon, oxygen, iron, in quantities that suggest multiple generations of stellar evolution have already occurred. But there has not been enough time for multiple generations of stellar evolution. Stars are born, live for millions or billions of years, die in supernovae, and scatter their heavy element products into the surrounding gas. The next generation of stars forms from that enriched material. This cycle takes time, enormous amounts of time. For early universe galaxies to already show this level of chemical enrichment, the first generation of stars must have lived fast, died young, and enriched their surroundings with extraordinary efficiency, more efficiently than any model of early stellar populations has predicted. There are also the little red dots. This is an actual scientific term used by researchers studying Webb data for a class of compact, extremely red objects detected in the early universe that do not fit cleanly into any existing category. They are small.
There is a way of thinking about this that frames it as failure. James Webb was built to answer questions, and some of the most important questions it was sent to answer — how did galaxies form? What is the true expansion rate of the universe? What does the early cosmos look like? — have come back not with clean answers, but with deeper, more complicated, more intractable mysteries. Under that framing, something went wrong. But that framing is wrong. Here is the truth about what James Webb has done. It has given science the single most valuable gift any instrument can give. It has shown us where the edges of our understanding actually are. Not where we thought they were. Not where our models projected them to be. Not the comfortable, theoretical limits we estimated from our armchairs and our simulations. The actual edges, located precisely by real data from the real universe.